Hi everyone, my name is Janhavi and this is my Lab 3 individual video report based on a black hole. So this lab is split into two parts. In part 1, I will analyze the star's motion to find the net force on the star for all points in the dataset using the starter code provided by the lab. I will then analyze the data and estimate the mass of the black hole. In part 2, I will simulate the motion of a spaceship around the planet and black hole by calculating all the necessary gravitational forces and using Newton's second law to predict the motion of the planet and the spaceship. I will then calculate the initial velocity for the spaceship to get close enough to the black hole without crashing into it and then leaving the system. Lastly, I'll go through some of my observations and additional questions based on my lab results. So here are some of the key concepts and formulas that this lab focuses on. So firstly, we have Newton's universal law of gravitation, and here are a few of the formulas that will help us calculate that. We also have Newton's second law, it's also known as the momentum principle. As you can see over here, F net is equal to dB dt, which is the same as change in momentum over change in time. We know that F net is equal to F net parallel plus F net perpendicular. We have these formulas here to help us calculate those values. We'll be applying this in part 1 by finding the measurements for the parallel, perpendicular, and net forces. And then we're going to use these, as well as Newton's universal law of gravitation, to calculate the mass of the black hole, specifically using this formula over here. Then we've also got the velocity update formula and the position update formula, which we'll be using mainly in part 2, in the computational model to predict the object's position and velocity as a function of time. So here's my GlowScript code for part 1. We have the email seed over here, which is generating a unique star trajectory. We also have entered in the given conditions for mass and time, given that mass is 2 times 10 to the power of 30 and time is 86400 seconds, which is equivalent to 24 hours. Under the while loop over here, we know that P initial is equal to the mass of the star multiplied by initial velocity, and P final is equal to the mass of the star multiplied by final velocity. Essentially, this is the equation of momentum is equal to mass times velocity. We're also calculating the star's change in velocity and change in momentum over here. We're calculating dB dt over here. We're using Newton's second law here with the formula that I talked to you guys about earlier, where F net is equal to dB dt. We calculate dB dt parallel here, and dB dt perpendicular over here, and then we also have F net perpendicular, and eventually over here in this final part of the code we're calculating the mass of the black hole by subbing these values and using Newton's universal law of gravitation. So here are my results for running my code and my computational model for part 1. Here's my value for mass, F net parallel, and F net perpendicular. So F net perpendicular in this video I'm about to show you is always pointing to the center of the orbit. F net parallel is always pointing in the direction of momentum. F net is the addition of both the parallel and perpendicular values. You can see that the arrow is pointing at its largest when the gravitational force is at its maximum value. So here's my GlowScript code for part 2. The goal for this part of the lab was to make sure that the spaceship was flying around the black hole without crashing into it or the planet. So the mass of the black hole over here that I've plugged in is the one that I calculated from part 1. Over here we also have these constants plugged in for gravitational constant, mass of the planet, mass of the spaceship, delta t, and initial time. We also have the initial conditions for the planet. Under the while loop over here, we've got these two sets of formulas. So essentially this first block of code over here, this part is calculating the change in position from the black hole to the planet and change in position from the ship to the planet, and then the gravitational force on the planet from the black hole and from the ship, and then the F net of the gravitational force on the planet is the addition of those two forces. And we do the same thing over here between the black hole and the ship, the planet and the ship, to calculate F net on the ship. We also then use the position and update velocity to update the position and velocity of the planet and the ship. And here are my results for running my code and my computational model for part 2. As you can see, the ship successfully flew around the black hole without crashing. And the final results over here do tell us that the calculations finished after 60 minutes, meaning it did not crash into the black hole or the planet. So here are some of my observations for this lab. The first question for what if discusses how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So these are essentially the same, only the calculations for them are a little different. We do know that F net is equal to change in momentum over change in time, which is essentially the equation F net is equal to dB dt, which is equal to mass times the change in velocity over change in time, which is equal to mass times acceleration. Hence net force and its parallel and perpendicular components are basically different, not different at all to the rate of change of momentum and its parallel and perpendicular components. So for what does it mean, we're answering what initial velocity would your spaceship need to have in order to enter some kind of orbit around the black hole. So essentially to calculate the value for this velocity, I would just do trial and error with different speed values and enter these into GlowScript over and over again until the spaceship enters into some sort of orbit around the black hole. Thanks for watching!